Civilization is based on materials. We need materials for electronics, for medicine, for biology, for energy applications. And if we want to keep developing, we need to make better materials, we need to make new materials, and we need to make new materials faster. What happened in the last 5 years is that the microscopes that we have started to produce immense amounts of information about the structure of material down to atomic level, about the functional properties, about the chemical composition. However, we have this information, but we don't know yet what to do with it. So one thing that we believe in is that applying computer technologies, big data, machine learning, artificial intelligence to the output of the microscopes in the form of atomic positions, local property, chemical information will provide us with a solid foundation to design and build new materials.
The new supercomputer that we're deploying now, Summit, is a 200 quadrillion adds or multiplies per second type of a machine, 200 petaflop machine. And these machines are costing on the order of $1 million per petaflop. So we're talking hundreds of millions of dollars. So only agencies like the Department of Energy that have these kinds of science missions and science needs can afford to deploy these kinds of resources. And so then these resources are made available to researchers around the world that actually are trying to solve these kinds of problems.
The way that you analyze data with these big computers have really pushed us into a realm where we really have to rethink the type of mathematics, the type of algorithms that we look to analyze these big data sets. And it really becomes a nexus where computer science, mathematics, and people that know what the physics are and what they're measuring have to come together and look at it as a team.
That's really the beauty of what IFIM is trying to do. IFIM is trying to bring all of that together. So, they're collecting data up at the institute. That data is coming down to our big supercomputers where we can do AI and where we can do the modeling and simulation. So we do all of that, and we're trying to have a workflow that actually allows all of that data to flow in a seamless fashion. That's the beauty of what IFIM is trying to do.
At IFIM, one of the main goals we have is to advance the area of chemical imaging. And what this is instead of just trying to look at how matter is shaped at the nanoscale, we actually want to know what its chemical constituents are. We want to be able to go to a location and know what molecules are there. If we can do that, we can then understand a whole lot more about the functionality of this material. And so we're developing new microscopes and new techniques that allow us to go to the nanoscale and not just look at the atoms that are there, but see how they're arranged and see the chemistries and the chemical behavior at the nanoscale. And now that we understand these behaviors, we can begin to optimize them. And we can optimize them and then synthesize them. So we can then use our knowledge of how materials behave, feed that into new synthesis techniques, such as operating at the atomic scale and building things atom by atom. And that loop will help us develop new technologies, new materials much faster.
It's been shown that you can move single silicon atoms through a graphene lattice, and graphene is just a 1 atom thick layer of carbon. And just a few weeks ago, here at the lab, we showed that we can take a few silicon atoms and stick them together to form few atom structures out of 2, 3, and 4 silicon atoms. And this is an exciting development because if you can build a material from the atom up, if you can specify which atom goes where in the material, you can come up with all kinds of new materials.
So our hope is that these tools that are being developed by IFIM become available to the broad user community. This user community can then gain more information about their materials, which in turn then allows them to not only understand better what materials do and how they interact, but also work towards application, works towards better solar cell, work towards better batteries, better electronic structures, and find solutions to many of the problems that we need to address.